This video is for our paper Hill Climbing with Trees that appeared in the 2020 International Symposium on Physical Design. I'm Patrick H. Madden, and this is joint work with my PhD student, Mohammed Kassani. We're both with the Binghamton University Computer Science Department. The problem we're looking at is on optimizing detail placement for integrated circuits. In the normal design flow, we start with global placement, which is usually performed by either analytic methods or recursive bisection, and this is followed by a placement legalization stage. At the detail level, the precise positioning of each circuit element can have an impact on wire lengths, circuit delay, routability. Local rearrangement for small problems can be easy, and you just try all different combinations and pick the best. As the optimization window gets bigger, though, things get much more tricky. With modern circuits, there are hundreds of thousands or even millions of standard cells in a circuit block, and detail placement is usually done with a sliding window, passing over a small region, optimizing as it goes. Typical window sizes are 6 to 8 elements to avoid a computational explosion, and the focus of the work we present here is on expanding the size of the window by an order of magnitude or more while keeping runtimes in check. To motivate the problem a little bit, let's take a quick look at some benchmarks that were developed a few years back. The PECO benchmarks are placement examples with known optimal configurations. Here's PECO 01. It's not a real circuit, but something generated synthetically, so that we know what the best possible configuration is, and we know what we can do with it. If we run the PECO circuits through standard circuit placement tools, the results are usually much worse than optimal, anywhere from 50% higher wire length to a factor of 2 or even more. On the global level, many placement tools do a good job putting cells into reasonable locations, and where we are seeing a considerable amount of loss is at the local level. Here's a very simple detailed placement problem. We'll assume we have a few cells that are fixed in the bottom, and that there are 8 other cells spread across 2 rows. We've only got a handful of interconnecting nets to make it easy as possible to see what's happening. It should be obvious right off the bat that this is suboptimal. The challenge is that without having a large window, and with many cells potentially moving, we can't find the optimal solution. For example, suppose we have a window size of 2 cells positioned over the top row. Both configurations of the cells have equal connection costs. We can trade crossing on the top for one on the bottom, but there's no net benefit. If we expand the window up to 4 rows, we still face the same problem. The connections to the cells outside of the optimization window act like anchors, holding the cells within the window to their original locations, or preventing the cells from moving to positions that would be better globally. Only if we expand the size of this window up to 8 cells can we get the best solution. With this example, it's easy to see what to do, but in real circuits, it's much more tricky. Here's the benchmark IBM 01 placed by NTU Place 3. There are some big macro blocks, a lot of standard cells, and they're all arranged into horizontal rows. The nets connected to each cell go off in multiple directions. Some of them are high degree, and they're all pulling in different directions. To find configurations that result in a net wire length improvement, the window sizes have to be large, but this typically leads to an explosion in the solution space. Finding a better placement is a lot like looking for a needle in a very large haystack. To briefly mention traditional methods for detail placement, one that is widely used is branch and bound. If we have a window that contains 4 cells, we can explore different arrangements with a depth-first search style tree. We might place cells A, B, C, and D, and then they get the wire length of this configuration. Then we'll backtrack, and then place D followed by C. We can backtrack again, and instead of B, we could place C at this spot and keep going. The key insight for branch and bound is that if we track the incremental cost of a placement, if it exceeds the cost of a known solution, we can prune the entire branch at that point. Branch and bound is usually used for windows of 8 cells or less to keep the runtimes in check. Moving beyond branch and bound, there's been some work using mixed integer programming and methods such as branch and price. The key idea here is to use a linear programming solver to find a lower bound on connection costs while exploring the solution space in a manner similar to branch and bound. Using the better estimates and good heuristics to select which branch to explore first, it's possible to increase the size of an optimization window. In an ASPD paper a few years back, we were able to solve 6x6 windows optimally in about a half an hour, but we're restricted to circuits with equal size cells, like the PECO benchmarks. More recent work out of Purdue has been able to handle windows up to 20 cells with varying widths, and with white space, each window typically taking a few seconds or less. Now let's focus on the new methods. While ILP gives a bit of scalability, it wasn't enough for the window sizes we were interested in using. Instead, we shifted our focus towards a heuristic approach that has its roots in the hill climbing partitioning work by Kernighan and Lin, and with a nod towards Bellman's dynamic programming. All right, let's go through a simple example of hill climbing with trees for detail placement. What we've got here is 16 cells arranged in a 4x4 grid. We're going to try to find permutations of them, and we're going to restrict the cells to their original rows. So A, B, C, and D can switch around. E, F, G, and H can also switch around. So lots of permutations, but everything's going to stay in the original row. The solution space for this example is actually fairly large. If we've got A, B, C, and D, that's going to give us 24 combinations, so 24 leaves at this level. Second level, where we're shuffling E, F, G, and H, again, 24 leaves from that. So it's 24 squared leaves on this level. Then we've got 24 cubed on the third level down. Final fourth level, 24 to the fourth power. Now we're going to do something a little bit unusual in how we draw our trees. Normally, you have your left branch, right branch, left branch, right branch. What we're going to do for this is rearrange each tree level by cost. So for instance, in this first level, if I have cost of 3 here, cost of 1, the better solution is 1. So we're going to move it over to this side of the tree, move 3 over here. Going to do the same thing on the next level down. 3 and 4, best solution, 7, 8 over here. You'll note that I've got edges crossing over each other. This is not how you would normally draw a tree, but is very helpful for understanding how our hill climbing with trees approach works. Now let's have a little bit of a thought experiment. We're going to go back to our original graph. So this is a tree with 24 to the fourth leaves. And if we're rearranging our vertices so that the best vertices are on the left, we've got what would be the optimal solution if we were to brute force the entire solution space down here. And the thought experiment is, if this is where our best possible solution sits, the question is, where would we find the parent of this vertex? And it's certainly possible that the parent of this vertex is a terrible solution on the previous level and a bad solution here, maybe a mediocre one here. This is certainly mathematically possible, but it's not likely. What seems much more likely, and what we can observe in practice, is we'll see paths that look something like this. Good solution here. Its parent is also a good solution on the previous level, and also a good solution here on up the tree. Usually the path to the best solution goes through a number of good intermediate steps. Think in terms of a race with lots of runners. The person who wins the race is frequently towards the front of the pack at the previous mile marker. And so this brings us to the hill climbing with trees sort of big picture. We've got the solution space that would be in place if we were to brute force the entire problem. Way too many leaves down here at the bottom. We're arranging things so that vertices are ordered left to right, and we've got this parameter k that says we will keep only the k best solutions. So we'll prune here to k at this first level, prune the best solutions or the k solutions we see here, prune the k solutions we have here. We're slicing off the section of the solution space, the part of the tree, that we think most likely has a good solution in it. Let's take a look at an example from a real design. We're extracting out of the benchmark IBM 01 that's been placed by NTU Place 3, a window of about 6 cells wide and 12 rows tall. Each row is going to vary a little bit because the cells are of different size. On the first row, we've got 5 branches. So this one over here has a savings of -2. It's better. Branch here is 0, no change in cost, and some branches that make things worse. We're calculating cost in an incremental way. And so this is the first level of the tree. Now let's look at how this thing grows out. This level spawns off more branches. So this is the second row. We're looking at a number of permutations here. And so they combine. Savings of 18 here, savings of 10 here. So this is this branch and then over to here. And we're coloring the ones that are good green, ones that are worse red. And so our tree grows out, and we're clipping and pruning at 16 vertices. So good solutions over the left, bad solutions over the right. You can see many places the lines cross over. So good solution here connects to a bad permutation, winding up over here. And as we build the tree, layer after layer, row after row, down here in the lower left corner is the best solution we found. Savings of 73 units. It has a parent in the previous row, still savings of 73. Over here, savings of 56, and 56 over here. And this is where the hill climbing comes in. If we were just applying a greedy algorithm, we'd select this row, and then select this row, and the one after it. But instead, we're keeping multiple branches, so even though this solution is not the best one that we're aware of, we keep it under consideration and it becomes a better solution later. So we're sort of crossing over hill climbing, going across a high point and finding a valley beyond it. And you can see this happen in a number of places. A simple greedy algorithm would always be choosing the best each step down. Here, something that's not the best moves back and becomes best again. It's the 13th best over here. This is the fundamental difference from a simple greedy algorithm. We're following a single track, and versus the hill climbing with trees, we're keeping multiple branches active all at the same time. So to quickly take a look at the pseudocode for our heuristic, it's very much like breadth first search. We have some initialization and building up the data structure so we can do our computations efficiently, and then the heart of it is really a for loop in the middle. We take a previous layer of our search tree, and then we combine it with new permutations for the next row. We do the cost calculations, throwing each configuration into a binary heap. We keep a heap simply because that makes it easy to keep track of the top k elements. Once we've finished all the layers, we go down and find the best solution, and we trace back up the tree to the root to find every configuration for every row. The code is relatively it's easy to implement once you have a good idea on how to do it. So we've got another little trick that we want to add to the code. In the previous example, we had 4 cells in a row, and we had 24 combinations. In practice, it turns out we don't need to do this. The incoming placement is usually quite good, and we don't need to make major modifications in order to find wire length gains. So if the incoming row has A, B, C, and D, we don't try all possible rearrangements. Instead, what we're doing is what we'll call partial permutations, where we keep track of how different a permutation is from the initial placement. So if I swap the positions of A and B, A moves 1 spot to the right, B moves 1 spot to the left, that's a net 2 units worth of change from the original permutation. We could also swap C and B, that will give us 2 units of permutation, or D and C. There are 4 different combinations that have a delta of 2 or less, the original, and then these 3 swaps. We limit delta in practice to a fairly small number, and this reduces the size of the solution space, but also keeps good quality results. So to drill in a little bit and give an insight onto why some of this works and the pruning in particular can be done. Here we've got conventional branch and bound. So we might place cell A, then cell B, then cell D, and come up with a configuration here, backtrack back out. But what's key to notice here is at this point, our incremental wire length contains only the nets connected to cell A. It is not comparable in any way to placing cell B. They have different nets, and the wire lengths between them, there's no way to make rhyme or reason or heads or tails of it. Contrast this to our hill climbing with trees approach. Here again, we've got a root node. We're expanding the graph out in breadth first manner. This vertex in our tree is a complete placement of cells A, B, C, and D. This vertex here is B, A, C, D. It is the same set of cells and the same set of connected nets. So you can have a roughly comparable measure between which one's better. You can look at these 2 branches, or these 2, or these 2, and make some semblance of a rational ordering. This is a big contrast with conventional branch and bound, or even branch and price, where no meaningful comparison between branches is possible. This lets us prune the tree to K solutions and still keep a good quality result. Now let's look at some experimental results. To demonstrate the impact of our approach, we performed a number of experiments on some standard benchmarks. To start off with, here's some results on running the method on a set of the PECO benchmarks. We start with the placement result of NTU Place 3 immediately after legalization and compare it to NTU's Place 3, including their entire detailed placement flow, which includes a number of different methods. In 13 of the 18 benchmarks, using our hill climbing technique alone, we obtained higher wire length reductions with runtimes running from a few seconds to a few minutes. We apply multiple passes of our approach with different window sizes until no further gains are found. On average, we're nearly in a percentage point better. If we apply our methods after NTU Place 3 detailed placement flow, we gain an additional 3%, indicating that the techniques from the two tools are complementary. Next up, let's take a look at the impact of the K parameter. If K is 1, our approach looks a lot like a greedy algorithm. If K is infinity, the approach would resemble brute force enumeration. Here, we're sweeping values of K from 1 to 1024 on the benchmarks PICO 18 and IBM 18. The numbers shown are gains for a single pass over the entire design. Note that as K increases, the wire length reductions are higher, but there's also diminishing returns. The trees are potentially exponentially large, but keeping only a small fraction is enough to obtain high-quality results. Let's go back to the tree example from earlier. The higher the value of K, the wider the tree is, in some sense. The best solutions, however, are clustered to the left, only occasionally dodging to the right. Keeping multiple branches prevents having a catastrophic error on any one level from destroying solution quality, but we also don't need to keep all of the branches. Modest values of K are enough in most cases. Now let's take a look at the impact of changing the delta value. We use partial permutations, and a delta of 2 is a single pairwise swap, while 2 swaps might give a delta of 4. The results might be a bit counterintuitive in that the lower values of delta, in other words, smaller changes to the initial configuration, are better. If you think in terms of the size of the solution space, however, it makes a bit more sense. Our optimization approach is heuristic in nature, and it's entirely possible to miss an optimal solution. As we increase the value of delta, the number of combinations increases exponentially, and we're looking for needles in progressively larger solution spaces. The problems just get much harder. In practice, delta values of 2 or 4 seem to work well, and they also give the best runtimes. In one more set of experiments, we scanned the designs using window sizes ranging from 2 by 2 up to 8 by 20. When the windows are small, more of them are needed to cover the design, and vice versa with large windows. With conventional methods, such as branch and bound, windows usually have 8 or fewer cells, and windows with 160 cells, like we have here, would be completely infeasible. The runtimes grow a bit with larger windows, but there isn't a computational explosion. And in terms of solution quality, we saw the best results with windows that are around 4 by 8 or 6 by 8, or somewhere between 30 and 40 cells. To summarize, our hill climbing with trees approach to detail placement in some respects resembles brute force, breadth first tree construction. In a departure from typical methods, we place sets of cells in each step and limit the number of permutations we consider for each set. By setting cells in this manner, we achieve a measure of comparability between nodes in the search tree. And because we can compare, we can also prune to K branches, and that keeps the runtime from exploding. We owe a great deal to the hill climbing ideas out of the partitioning community. Where Kernighan and Lin used locking of vertices to push search into new areas, we keep multiple branches alive, achieving the same objective. In some respects, we're not just hill climbing, but going over the mountain, looking for good solutions in between the ups and downs of a complex cost surface. Runtimes from our approach are near linear, and the techniques we present here are complementary to conventional detail placement methods. There are a lot more details in the paper, so we encourage you to go check it out. It's available in the ACM Digital Library, and here's a QR code that should take you right there. Or if you've got questions and want to drop us an email, you can find us on the web at optimal.cs.binghamton.edu.